Welcome, my name is Hiram, and in this video I will show you an idea about how to build cockroach systems, or in other words, data systems that survive apocalypses. Let's get started. The idea is very simple, to develop a platform to build distributed systems quickly and effortless. The platform will take care of the concurrency, low latency, fault tolerance and redundancy matters, allowing developers to focus on solving only the business problems. In the middle, we'll make an interesting stop on how to build decentralized systems with the same platform. The idea is to make a clone of the GitHub business model, but giving it a huge twist. Like you probably know, GitHub allows developers to store Git repositories and create continuous integration and delivery pipelines. A Git repository has what is called hooks, which developers can use to attach scripts to run tasks in their repositories. Everything from preparing commit messages, running tests, updating dependencies, etc. can be done with the help of hooks. Once a developer successfully pushes a commit into GitHub, all kind of magic happens. Yes, magic, because developers can create customized pipelines to do any kind of post-processing that their applications require. Brilliant, but that already exists, so what's the huge twist then? The twist is that the platform will not process source code changes from developers, but instead will process data changes from end users. That's right, the end users will push data changes, not in the form of files and folders, but in the form of primitives and trees. You can think of this as Git for web browsers, where users commit data changes in their local repositories and push those changes into the platform. This is done with the help of the ASP.0 framework. ASP.0 is an implementation of Git repositories and Git hooks programmed in JavaScript, Ruby, and soon in Elixir. The framework allows end users to commit data changes in local repositories. The framework also allows developers to attach specific processes called picoservices in the different stages of a data commit. The platform in its turn receives and processes the data commits, and after successfully updating a repository, ta-da! Customized pipelines will take care of the data, and the magic of aspects and nanoservices will do the rest. A Ruby implementation is already in place, but soon it will be replaced with an Erlang implementation. The reason is simple. The Ruby interpreter has the same problems as the Java virtual machine and the common language runtime. They are not ready for the concurrency, low latency and fault tolerance challenges of distributed applications. Erlang, on the other hand, was designed from the beginning to cope with those kind of constraints. For accuracy's sake, it's actually Elixir what I will use instead of Erlang, since it has a more approachable and modern syntax. When the end users successfully push their data changes, the platform will replicate the data in a network of interconnected nodes. These nodes will be hosted in different cloud services in order to maximize the availability. If any of the cloud services fails, then the other cloud services will take care of the total workload. The aspects will also be deployed in a network of interconnected nodes. An aspect can mistakenly be grasped as a microservice, but it differs in every single way from a microservice. It is closer to a plain function. Aspect is just a shorter name for supervisor of nanoservices. This is what I call the special case of the platform, when it's possible to build decentralized systems. But what about the general case then? How is it possible to build distributed systems with this technology? The answer is simple. In the previous implementation, we could see that the platform is divided into frontends and backends. Frontends, like web browsers or native applications, push data changes into backends, and only backends are allowed to trigger nanoservices. But in the general case, there are no frontends nor backends. Instead, there are locals and remotes, and both are allowed to trigger nanoservices. This is possible with the help of the Web Application Messaging Protocol, which allow web browsers to behave as backends. So, in the general case, it will be possible to push data changes from a web browser directly to another web browser. In the general case, routing data through cloud services is not necessary. All cloud services could be unavailable, and the system would still work since the data will flow at the edge of the cloud. So the system could survive an apocalypse. Let's make a comparison between microservices and aspects in order to prevent confusions. Microservices are stateful with a database at the center. They have many endpoints, and these endpoints have different types of inputs and outputs. Aspects, on the other hand, are stateless. They have only one endpoint and the input is constant. An aspect, which is a supervisor of many identical nanoservices, receives an address as input. That address tells the aspect which repository, which commit, and which node in the data graph it has to operate. In microservices, the data boundaries are explicit. There is no orphan or shared data, and therefore they are data-centered. With aspects, on the other hand, the boundaries are implicit. Many aspects read the same data, and there is data that no aspect reads at all. Aspects are totally function-centered. Microservices are stateful. Aspects are stateless, so restarting a nanoservices is a no event. Microservices have many endpoints with customized inputs and outputs. Aspects have only one endpoint with a fixed input, an address, and a fixed output, whether it is starting a process or saving a commit in a repository. Microservices can be seen as the top expression of object-oriented programming, whereas aspects can be thought of as the top expression of functional programming. Microservices are about data segregation and function integration. Aspects are about data integration and function segregation. Microservices are deployed as data islands connected in a serial fashion. Aspects are deployed in a network of peer-to-peer nodes and they are isolated from the repositories they operate. Repositories are also deployed and replicated across different nodes in many cloud services. If a cloud service is unavailable, there will be other cloud services that will take over the workload. Last comparison point. In microservices, the nodes are typically interconnected in a serial entire architecture. This architecture is simple to visualize, but each node is in reality very complex with many functionality layers. In aspect-oriented architecture, the complexity of the system is exposed, but every single part of the architecture is simpler. The commit pipelines, the repositories, the adversary and Kafka brokers for redundancy, and the adversary aspects for business logic. All are much simpler to define and explain because they do one thing: they are more generic and easier to implement. And this is how data systems could survive apocalypses. In this kind of distributed systems, the cloud would only be a fallback or a backup. The data would flow through nodes at the edge of the cloud. Because the cornerstone of this technology is the immutable logs or repositories implemented with Merkle trees, just like cryptocurrencies or Git does. And now, the credits. If you think this is an interesting idea and you would like to join the development team, or if you are an IT tycoon that would like to increase the chances to become the next Jeff Bezos, drop a line to my email and let's make this happen. Stay tuned for the demo of adversary in a web browser. See you!